going to take a look at dependent events. It's basically the same as independent events as far as the multiplication step once we have our probabilities. However, because one outcome does affect the probability of the next one, we need to make sure that we are taking it one step at a time to find our probabilities. I'll show you how that works. We have a hand of 2 cards that's dealt from a standard deck of cards. What's the probability that both cards are clubs? Assume that the cards are not replaced. And that not replaced assumption there is something you're going to see a lot whenever we have dependent events, because the first event does change the probability of the second one. Whenever you have a standard deck of cards, you have 52 cards. When they ask how many cards of one suit, such as clubs, that's going to be 13, 1/4 of the cards, and so 1/4 of 52 is 13. So the probability that the first card is a club is just going to be 13 over 52. So we'll write that in here. However, because we're not replacing it, we're changing our numbers here. We no longer have 13 clubs and 52 total cards. We only have 12 clubs because we took one out, and therefore only 51 total cards. So when we take our second club, I meant to say club here, given that we already pulled a club, we have different probability now. We have this 12 here out of 51, and that's what we're going to have here, 12 out of 51. In the same way that the first time through we had different probability. So once we have those two numbers, we just multiply them together the same way we did above. So 13 out of 52 times 12 out of 51 is going to get you a big ugly fraction that will reduce down to 1/17. And that will be your answer. Next one here, we have a cup on your desk that has 4 red pens and 5 black pens. And so what I did here is I sketched out, we have 5 black, 4 red, and a total of 9. What is the probability of her selecting first a black pen, then a red one? Well, let's go ahead and start with the one that we're given then. So we have 5 black pens and 9 total pens. So our probability is just going to be the number we want out of the total, 5 out of 9. So the probability of a black pen, 5 out of 9. Now because we pulled one black pen out, we have to modify our numbers. So we're down to 4 black pens and 8 total pens. Our red pens did not change. So the probability now of getting a red pen, given that we have already pulled a black one before, that's why I wrote it, probability of red given that a black one is gone, is just going to be what we have left. We have 4 red pens out of 8 total. So 4 out of 8. I'll highlight this in pink so you know where this came from here. Just as above, we're going to take those two numbers once we have them and multiply them together. And that's going to give us eventually 5 over 18. So our probability is 5/18. Third example that we have here is a bunch of coins. There's 3 quarters, 5 dimes, and 8 nickels in a piggy bank. Suppose that we take out 3 without replacing them. So we're going to keep the 3 coins out as we pull them. What is the probability of selecting a quarter, then a nickel, then a dime? We're going to start with the quarter. Probability of getting a quarter is the number of quarters out of the total. So 3 out of 16. Now let's update our numbers. We took out a quarter and we took out 1 from the total. So we're down to 2 quarters and 15 total. The next one, we're pulling a nickel. Well, we have 8 nickels and 15 total left. So the probability of getting a nickel at this point is 8 out of 15. So 8 out of 15. And then finally, we have a dime. So we have, Oh, before we move on, always remember to update your probabilities so you don't get confused later. We're down to 7 nickels and 14 total. So then we have our dime. We have 5 dimes and 14 total remaining. So we're going to have 5 out of 14. So we take these 3 numbers that we got. That last probability was the 5 out of 14. The second one, the 8 out of 15. And the first one, the 3 out of 16. Multiply them all together. And that's going to reduce down to 1/28. So the probability of this event happening, this multiple step dependent event, is 1/28. Next section, we're going to look at adding probability. The basic rule says that whenever you have 2 mutually exclusive events, we'll talk about what that means, you just add the 2 events together to get the probability. And when you have 2 events where there is some overlap between the events, you do exactly the same thing. You add the 2 together and you subtract when they both happen. Now let's take a look at what that means. First, let's try to understand mutually exclusive events. So we're going to look at each of these and decide if it's mutually exclusive. A bag contains 35 eggs. 15 are yellow, 10 are red, and 10 are blue. What's the probability of selecting a yellow or a red egg? Because there is no possible way to get an egg that is yellow and red, to get that overlap, they're separate, so it's mutually exclusive. What that's really saying is that there's no way that these 2 events can happen at the same time. You're either going to get a yellow or a red, but you can't get a yellow and red egg. And you'll see examples that do have that, and I think you'll understand what that means then. Next one, a pair of dice is rolled and the 2 numbers are added. What is the probability that the sum is a 5 or a 7? Again, that's going to be mutually exclusive because you can't get a sum that is both 5 and 7 at the same time. That doesn't make sense. So this is mutually exclusive. This example here, what is the probability of drawing a red card or an ace from a standard deck of cards? Well, there is an overlap there because you could draw a red ace. And in that case, it would be both a red card and an ace. So that is an inclusive. Next one, a bowl has 20 wheat crackers, 16 sesame crackers, and 14 rye crisp. The person picks a cracker at random. What is the probability of picking either sesame or rye? Since there's no way to get 2 different types of crackers in the same pull, it's mutually exclusive. You can't pull sesame and rye in the same pull. 3 cards are selected from a standard deck of 52 cards. What's the probability of selecting a king, a queen, or a red card? Well, king and queen are different. They're mutually exclusive, but as far as the full set of these, you could have a red queen or a red king, and that would overlap with the red card. So we do have inclusive right here. Finally, a pair of dice is rolled. What is the probability that the sum is odd or a multiple of 3? Well, we know that multiples of 3 are, some of them are odd and some of them are even. So there are times when these are going to overlap. In fact, the number 3 is one of those times. So in that case, because it could happen, because both the events could happen at the same time, it's inclusive. Going down here, adding mutually exclusive events. Let's go ahead and practice this. The example here says, to choose an afternoon activity, summer campers pull slips of paper out of a hat. Today there are 25 slips for a nature walk, 35 slips for swimming, and 30 slips for arts and crafts. What's the probability that a camper will pull a slip for a nature walk or for swimming? Well, since there's no way to have 2 slips happen at the same time, they're mutually exclusive. And if you add up the numbers, there's a total of 90. So what you're going to do is you're going to take the probability of the nature walk plus the probability of swimming, and if you add them together, it's going to give you the probability of nature walk or swimming. And that adds up to 60/90ths, or 2/3. So let's do some more practice here. When you have mutually inclusive events, you have to do that extra step that I had mentioned earlier. So what is the probability of drawing a face card or a black card from a standard deck of cards? Well, a face card could be black or red, so there's a chance of overlap. So there's, the way they wrote it here I don't particularly like. They wrote it as 3/13 for the probability of a face card, but in general that would be 12/52 because there's 12 face cards in the deck. Plus the probability of a black card, there's a 50% chance of that happening. And then you subtract out how many black face cards there are. There's 3 of them. And so that would give you your probability. But let's do some more examples of our own here. Find the probabilities. These are the same things we did before, but now we actually have to find the probability. A bag contains 35 eggs. 15 are yellow, 10 red, 10 blue. What's the probability of selecting a yellow or a red egg? Well, we have yellow eggs and red eggs. If you add them up, the total 15 plus 10 plus 10 is 35. So the probability of getting a yellow one is 15/35. And the probability of getting a red one is 10/35. So probability of yellow plus the probability of red. We said 15/35 for yellow and 10/35 for red. And the reason we're adding is because that's what you do when you have mutually exclusive events. So we add them together, we get 25/35, which reduces to 5/7. Next one, a pair of dice is rolled, 2 numbers are added. Probability that their sum is a 5 or a 7. For the purposes of this video, I'm not going to go into how you find those probabilities, but just get the basic idea here that you need to find what is the probability that you get a sum of 5 and add it to the probability of getting a sum of 7. And it happens to be 4/36 is your probability for the first, 6/36 for the second, and if you add those together you get 10/36, which is 5/18. This next one is our mutually inclusive example. What is the probability of drawing a red card or an ace from the standard deck of cards? Well, first we take the probability of drawing a red card and we add it to the probability of drawing an ace. But because it's inclusive, we have this extra step here. We have to subtract anytime there's overlap. So we subtract the number of red aces. Let's start. We know we have 52 cards in a deck. Half of them are red, so that would be 26/52. That's the probability of our red cards. Next, we have probability of getting an ace. Well, there's 4 aces in the deck, so we add in the 4/52. Probability of getting an ace, 4/52. And finally, how many red aces in a deck? Well, there's 2 of them, so we subtract 2/52. So that's the extra step here, because it's inclusive. And when we add that all up, we're going to get 28/52, which will reduce down to 7/13. That's the probability of getting a red card or an ace from a deck of cards. You can try it yourself if you're curious. D. A bowl has 20 wheat crackers, 16 sesame, and 14 rye. It's the probability of picking either a sesame or a rye. Well, we have sesame and rye, and since this is mutually exclusive, we don't need to subtract anything. Probability of getting a sesame is 16 out of the total, so 16/50. Probability of getting a rye is 14 out of the total, so 14/50. Add them together, 30/50, which is 3/5. Next one here, 3 cards are selected from a standard deck. It's the probability of getting a king, a queen, or a red card. Well, let's get our king, our queen, and our red card, and let's subtract all the possible ways of duplicating. So we subtract our red queens and subtract our red kings. So we have 5 things we need to know the probability of. Probability of getting a king, 4 kings in a deck, 4/52. 4 queens in a deck, 4 out of 52. How many reds? Half the deck we said, so 26 out of 52. Now we're subtracting. How many red queens? Well, there's 2 of them. And how many red kings? 2 of them. So if you take all these numbers, add them together, we have 4 plus 4 is 8, plus 26 is 32, minus 2, minus 2. Oops, I'm at 34, minus 2, minus 2 is 30 over 52, and that reduces down to 15/26. So probability here is 15 out of 26. And we're going to skip this last one. And I'm just going to give an overview of Venn diagrams here. You've probably seen these in other classes, but basically what you're looking at is there's the probability that one thing will happen, probability that the other thing will happen, and there's this region in the middle where we're saying that both happen. And so when we talked about, for example, a probability of a king, so let's say probability of a king over here and probability of a red card here, in the middle you would have the probability of the red king. And that's what they're referring to when they have a Venn diagram like this. We have some type of event, another type of event, and in the middle is where both happen. So for example, Venn diagram at the right shows the number of juniors on varsity sports team at this particular high school. Some athletes are only fall athletes, some people only winter, some people only spring, and then we have special cases. We have one person who's spring and winter, 4 people who are fall and spring, and 3 people who are fall and winter. And you see that their number falls in the overlap between the fall, which is here, and the winter, which is there. So because it falls in between those two, it's only those two. And there's this last special group in the middle, these 5 people who do a sport in all 3 seasons. And you'll see that number 5 falls within all 3 circles. And then all the other numbers out here, these people just do sports in one of the seasons. Same thing down here. You have people that only like classical, only like 40s pop, and only like country and western. You have people who like 2 of these, so either these 2, or these 2, and then you have some people, 6 of them, that like all 3 of them. And so when you're doing a 3-way Venn diagram like this, that's how you would fill it in.